Good afternoon, everybody. My name is Christoph SCHNÖLL from BODO MÖLLER CHEMIE, and it's a pleasure to be here today, this afternoon, and to talk to you about an innovative curing technology for epoxy resins. Let's take a couple of seconds and have a look at this picture I'm showing here. This was taken in our headquarters, in our storage area in Offenbach, and what you can see here is the chemical structure of bisphenol A diglycidyl ether epoxy resin. And that's exactly the topic I want to talk to about epoxy resins and a new and innovative way of curing them. But before we start with this technology, I'd like to take the possibility to highlight a couple of challenges and trends we see in the market right now. On the one hand, of course, we want to increase efficiency. Want to increase efficiency in terms of performance of our end products. We want to have a more efficient way of production, and also we want to decrease costs. Then, what we just heard in the last session, reducing CO2 emissions, of course, is one of the hottest topics at the moment. And we can do that, for example, if we build lightweight constructions. So this is one reason why composite materials will also be very important for innovative future production. And then we can also, for example, have an enhancement of the lifetime of our products. So what we need, therefore, is a very durable materials. And this durability already also leads me to the last part. Of course, safety is also a very important subject here. Like I mentioned already, durability and also important for safety aspects. We want to have systems with outstanding thermomechanical properties and therefore very good temperature stability. And within my talk, I will present this new curing technology that will show you that we can really have high thermomechanical properties, good durability, and therefore also enhance the lifetime, for example, of materials. But before I dive right into, please let me take the opportunity to introduce you to BODO MÖLLER CHEMIE, who we are and what we do. So we are a global specialty chemical distributor, but we see ourselves more as a solution provider. We have very deep knowledge and know-how about products, applications and markets, and we use this know-how and knowledge to serve you, our customers, to find the best solution possible. And one very special thing we do is we take the chemical information that's within an epoxy resin, for example, or an adhesive, and we translate it into mechanical engineering data, or also electromagnetic data. So you guys don't have to worry about the chemistry anymore. Let us take care of that. And last but not least, we also focus on megatrends. And that's exactly why we are here today. We focus on composite materials, for example, for the transportation, automotive, also for the aerospace industry. And some facts and figures about BODO MÖLLER CHEMIE. As I already mentioned in the beginning, we are a global organization with more than 40 locations worldwide. We have more than 150 highly trained and educated technical sales engineers. And this combination of our global setup with the know-how of our salespeople within our company is one of the reasons why we have decade-long partnerships with these market leaders you can see on the slide here. But I would say that's enough about BODO MÖLLER CHEMIE. Let's dive into today's subject of epoxy resins and innovative curing technologies. I guess we all here are quite familiar with epoxy resins. This is a high-end thermoset material for advanced applications. And this is also the reason why epoxy resins have been used decade-long in different kinds of markets and applications. That can go from aerospace to automotive, but also mobility, sports and leisure. And as we can see here, it feels like on every second booth there is a hydrogen pressure vessel. So this is really also an up-and-coming market for composite materials. And right now it looks like that carbon fiber composites are the only solution that can serve this market here. And last but not least, of course, also adhesives are a very special and good market for epoxy resins. Bisphenol A, diglycidyl ether, is by far the most common epoxy resin on the market. Short here is batch. I already introduced it on my very first slide here, again, the chemical structure. And although this material is really widely used on the market, and it's by far the biggest epoxy resin when it comes to worldwide production, this system also comes with certain kind of limitations. With a limitation, for example, when talking about the thermomechanical properties and the glass transition temperature. To shortly explain, the glass transition temperature, or short TG, that's the temperature where thermoset material changes from more glassy behavior to the rubbery state. And it's a very important indicator for the temperature stability of materials. And to go more into detail why there is a limitation here, let's have a look at different kinds of chemistries and technologies that can be used to cure epoxy resins. So on the one hand, for example, we have diisocyandiamide as a latent curing system, which is often used for prepreg applications. And we see if this curative is used solely with bisphenol A-based epoxy resins, we have a glass transition temperature and a limit there of around 125 degrees. The best right now we can go to with the classic curatives is aromatic amines, where we can see that we can reach 180 degrees as a glass transition temperature. Nowadays, if you want to formulate systems with higher glass transition temperatures, of course that's already possible, but then you have to use multifunctional or tetrafunctional epoxy resins. Those can be quite expensive, and also you could get into trouble when it comes to viscosity. So therefore it would be interesting if there is a solution on the market that can be used for normal bis A epoxy and to reach higher thermomechanical properties, higher glass transition temperature. And now the question is if dianhydrides can do better when talking about mechanical properties, durability, and glass transition temperature. And that's why I would like to introduce to you today BTDA, Benzophenonetetracarboxylic dianhydride. We are talking about a solid powder, molecular weight of around 322 grams per mole, and an anhydride equivalent weight of 161 grams per equivalent. And this is an outstanding curative for epoxy resins. What you achieve is thermoset materials with very high temperature stability and also really good electrical insulation properties. To be honest, this system is already widely used, or this molecule is already widely used in polyimide synthesis. But today I want to focus my talk on the epoxy chemistry and show you what can be done with this kind of curative with epoxies. But to better explain the possibilities and the way this system works, let's go one step back and have a look at how anhydrides, also classical liquid monoanhydrides, cure an epoxy resin. Basically here we have a two-step reaction. In the first step of the reaction, the anhydride reacts with an hydroxy group in the epoxy resin, and then we have another step, and there the anhydride reacts with our epoxy group. And this step is critical and also important for the curing and the network formation of our epoxy network. So what is quite important here is that with anhydrides, out of a difunctional epoxy resin, you create a tetrafunctional reactant because you have this two-step reaction. But those are classical anhydrides, monofunctional anhydrides. If we now go to the BTDA, we see that we have a dianhydride. So that means we have a tetrafunctional reactant when it comes to the curative, and then also we have the tetrafunctionality when it comes to the epoxy resin. So with this very high functionality, multifunctionality, we have the ability to create extremely high degree of cross-linking, and therefore we get outstanding material properties when it comes to high glass transition temperatures, high thermomechanical properties, very good durability of our materials, very good chemical resistance, and also very good electric properties. Let's go a little bit into detail how to work with this BTDA. First, we have to look at the stoichiometry, how a system using BTDA and epoxy resin should be formulated. So basically what we would think is that we have to have a stoichiometry of the anhydride and the epoxy ratio of being 1:1. So we have one epoxy group that can react with one anhydride group. But this is not perfectly true for those dianhydrides. What we saw for long R&D work is that here it is much better if you have a ratio of anhydride to epoxy which is far below 1 to get the best performance out of your thermoset system. And to have more details here, the best performance you get if you have roughly a ratio of 0.5 anhydride to epoxy. So you need really a high excess of epoxy resin to achieve two things. The one thing, for example, is that you promote homopolymerization of the epoxy resin, which leads to very good mechanical properties because a different kind of polymeric network is formed. And the second reason why you want to have an excess of epoxy resin is that you take care that you don't have any unreacted anhydride groups on the one hand. Also, you take care that you don't have an over cross-linking in your system, which might be a problem. And you reduce the impact of premature vitrification, for example. And here I would like to provide even more detailed information on how to process BTDA formulations. So basically what we need in a very simple epoxy formulation is of course the bisphenol A based resin. We use the BTDA dianhydride curing agents. You can add some fumed silica if you want to play around, for example, with the viscosity. And also, it's not necessary, but you can use catalysts, for example. The catalysts then can reduce, on the one hand, maybe the curing temperature, but also the curing time. And here we see there are different kinds of catalysts that can be used within this chemistry. That can be some kind of ammonium salts, but also different imidazole derivatives are great solutions here. And now in the last couple of slides, I already talked a lot about how great performance and what can be achieved, but now I would really like to show you some results that we have from the lab. For example, if you have a formulation that is based on bis A epoxy and ethyl-methyl imidazole as a catalyst and the BTDA, we see that we get thermomechanical properties that are with a glass transition temperature in a range of close to 240 degrees centigrade. And please keep in mind, I know it's not special to have an epoxy resin formulation with a TG of 240 degrees, but it's very special to have such a formulation that is solely based on bisphenol A epoxy. There is no kind of multifunctionality inside. There is no kind of tetrafunctional epoxy resin. This is bisphenol A epoxy with this curative, and it allows you to achieve such high crosslinks, such a great network, and also therefore the high TG values. Of course, there are also some topics to keep in mind when formulating such BTDA-based epoxy systems. One possibility, for example, is to disperse the curing agent in the liquid epoxy resin. Like I mentioned before, we are talking about a solid material. It is not completely soluble in epoxy resin. So what you need to do is you need to disperse it in the liquid epoxy resin. You can use, for example, different catalysts or also additives, and then you form a paste which is ready to use and, for example, can be perfectly used for toe preg, pre-preg applications, also adhesives. But you have to keep in mind that storage stability at room temperature is not perfect, so it needs to be used more or less right away and need to be mixed in time. But stable 1K formulations are also possible. They need to have different kinds of considerations. Maybe you have to go down a little bit with the storage temperature, but then they also should be stable for a longer time. But of course, we also see in the market multiple different applications that have needs, for example, for lower viscosities, or they want to have a better way of storage stability and way of packaging. And that's the reason why, of course, there's also the need for 2K formulations, which can be also achieved with this curative. With 2K formulations, for example, it's possible to take this solid dianhydride and to formulate it into classical monofunctional liquid anhydrides. And this then can be perfectly mixed with a ready-to-go epoxy resin. And what we achieve here now is that on the one hand, the liquid anhydride acts more or less as a reactive diluent. It helps you to lower the viscosity of your final formulation, and also it helps you to prevent the possibility of over-cross-linking within your network. And this 2K approach is a great way to have solutions, for example, again, for composite materials, but also for adhesives or, for example, molding compounds or different kinds of encapsulations. So to sum up this technology a little bit, what we can show here is that it is possible using solid dianhydrides and bisphenol A epoxy resins to form really high performance thermoset materials with exceptionally high glass transition temperatures that can go up to 240 degrees. And also keep in mind, this 240 degrees, this is not the limitation, because if, for example, you take these formulations and add then some multifunctional epoxies, you can maybe even go higher when it comes to thermomechanical properties. And this good network formation and crosslink density then also gives you a very good durability of your materials, which is of course important when we talk about sustainable handling of end materials, because we all know recycling is a very big topic when it comes to composite materials, and a huge challenge. Unfortunately, I cannot present a solution for recycling of epoxy composites, but what I can present you a solution that makes the composites that we produce even more durable, so we can use them for a longer time and have a better lifetime, which is also good for sustainability. Yes, so I'm already at the end of my talk. I hope I could show you that we at BODO Möller Chemie are always providing high-tech solutions, state-of-the-art technologies, and we are really ready to be a part in innovative future technology, and we would enjoy doing this together with you, our customers. So I would say let's partner up and make it happen together. And yeah, last but not least, thank you very much for your kind attention. If you have any further questions, I think we have a couple of minutes left now, or otherwise I also invite you to our booth. Come to us, we are here also in Hall 6 and 24, and I'm happy to talk to you about this technology and also the other solutions we provide. Thank you very much. Any questions? Okay, so like I said, if it's not the case right now, I'm happy to invite you to our booth. We will be here. I will be here today and tomorrow, but also my colleagues have great knowledge about this technology. So we are happy to explain further and answer any questions you have. Thank you very much.